Christian will tell us about max entropy distributions and how to beat 50-year-old problem.
Thanks. All right, so yeah, I'm going to talk about analyzing the algorithm for TSP. It's going to be based on joint work with a few people, so I'll point them out as I go along. All right, so what is TSP, or the traveling salesperson problem? As input, we're going to get a set of points, V, along with a metric, which is symmetric. Okay, so I like to think of this as the complete graph where I have some weights on the edges.
So Misha, I'll try to remind you too, for the Zoom and the recording, you can write a little bit.
A little bigger than this? Okay, I will try, yeah. Yeah, so here's an example input. And again, I'm just going to always think of a complete weighted graph. So maybe all the edges have cost 1, except this edge has cost 2. And now what you want to find is a minimum cost Hamiltonian cycle in this graph. Okay, so for example here, this is the optimal solution, has cost 4. Right. Okay, and it turns out that an equivalent output you could look for is just a multi-set of edges that connects the graph and has even degree at every vertex. So, for example, this wouldn't be an optimal solution, but I could also have returned this. That would be equivalent. And the reason is that, well, this graph with this multi-set of edges is Eulerian. So it has an Eulerian tour that visits every edge exactly once. And using the triangle inequality, I can just shortcut this tour to get an actual Hamiltonian cycle. Right, so if I were to sort of do this in this graph, maybe I'm going 1, 2, 3, 4, 5, and 6. Right, I can go, my Hamiltonian cycle will be 1, 2, 3, and then 4. And then instead of going back to 5, I can delete these edges and replace it with this edge. And by the triangle inequality, my cost hasn't increased. Okay. All right, so I'm gonna go through a kind of long history of this problem, and that's going to be sort of the first half of the talk. We'll see how many questions there are, and maybe more than the first half.
Just sorry, this multi definition, do you care for minimality or?
Yeah.
Yes, sorry. So this should also be this is sort of equivalent in terms of finding the Hamiltonian cycle, but yeah, it should also be a minimum cost. Thanks. Okay, so I'm going to go through history. And there's a lot of things I'm going to leave out because there's a lot of work on this problem. But I'm really going to focus on sort of the general case where this metric has no restrictions. It sort of begins in 1972 when Karp proved that metric TSP is NP hard. Okay, and I'm lying a little bit. What Karp actually proved is that Hamiltonian cycles NP complete. But it's sort of immediate to see that this means that metric TSP is NP hard. Okay, the next thing that happened in 1976, 1978, Christofides and independently Serdyukov behind the Iron Curtain found 3/2 approximation algorithm for the problem.
I guess factor 2 was sort of.
Yeah, you could put that in there.
Problem.
Yeah. Yeah, there's a really nice factor 2 approximation for this problem where you find a minimum spanning tree and you double every edge. So the first maybe like non-trivial approximation algorithm was this. I don't know when the double tree algorithm is from, actually. Is it, yeah, okay. Right, so what is an approximation algorithm? Let's just get that. Everyone's on the same page. So we're going to say a polynomial time algorithm is a, I'm going to put kind of the randomized definition in parentheses so you can read it with or without it. So the polynomial time is a randomized alpha approximation if it returns a solution of cost at most alpha times the cost of the optimal solution on all inputs. Okay. And for the randomized version, you just need to do this in expectation. And you can run the algorithm kind of many times to get this with, say, high probability. So let's actually do this 3/2 approximation by Christofides. I think probably many of you have seen it, but I think it's a good warm up. Okay. All right, so the first thing I'm going to do is find a minimum spanning tree of the graph. So let me use this graph as an example. Here's one of the minimum spanning trees. That's cost 3. Okay, now like let's work with this definition. We want to have a set of edges that connects the graph. All right, we've done that. But we want every vertex to have even parity, right? An even number of edges in that subgraph. So let's just do let's kind of fix that. Let's add the minimum cost O join, where O is the set of odd degree vertices of T. And let me define O join in case you haven't seen it. I'll do it. Here. So for a set of vertices O of even parity, an O join is a set of edges F such that for all vertices in O, they have odd parity in the O join. And for all vertices not in O, they have even parity. Okay. And this can be computed in polynomial time. Actually, one way to do it is to find the minimum cost perfect matching between the set of vertices and O. But actually, this is a little bit more convenient for us. Okay, so in this example, all of the vertices have odd parity. So a minimum cost O join would look like this. And now we get some solution of cost 5, whereas the optimal had cost 4. Okay, so now let's see why this is a 3/2 approximation. Let's see if I can do it here. It's pretty quick to see. All right, so the first thing I want to argue is that the cost of the minimum spanning tree is at most the cost of the optimal solution. This should be pretty clear. The optimal solution is connected, so it contains a spanning tree, and we're finding the cheapest spanning tree. Second thing is almost as easy. That the cost of the join is at most half the cost of the optimal solution. So why is this true? Well, let's look at the optimal solution. Some Hamiltonian cycle, where I'm using the equivalence between these two definitions. And let's just circle the odd degree vertices in red. There should be an even number of them by the handshake lemma. But now I can actually partition the edges of the optimal cycle into two joins, two O joins. Right, so here's maybe J1. I did that wrong, sorry. And here's J2. Okay, and obviously the sum of the cost of the optimal solution is equal to the sum of the cost of J1 and J2. So one of them has cost at most half of the cost of the optimal solution, and we just find the cheapest one. Okay, so that's the whole proof of Christofides' algorithm. Okay, let's move forward a little bit in time. 1980, Woolsey showed that integrality gap of the subcore polytope is at most 3/2. What's the subcore polytope? Keep track of my polytopes over here. Hopefully this isn't too small. So it's sort of the obvious thing is I'm looking for kind of a fractional Hamiltonian cycle. So every vertex should have degree 2. That's encoded by this constraint. Remember, delta V is just the set of edges adjacent to the vertex V. And then every cut.
Variables are on the edges.
Variables are on the edges, yeah. Made a variable xe for every edge of the graph. And then I want all the cuts in this graph to have at least 2 edges going across them. This is also true of Hamiltonian cycles, right? And now if I made these variables binary, this would actually be the convex hull of Hamiltonian cycles, integral Hamiltonian cycles. But I've kind of relaxed this condition and I've allowed them to just be fractional. Okay. So that's the subtor polytope. Oh, and I should say, we have the kind of counterpart, which is the subtor LP. And this is just, I'm going to minimize the cost of your point X subject to X lying in this polytope. And we can solve this problem in polynomial time because even though we have an exponential number of constraints, this can be separated in polynomial time. Okay, now what is the integrality gap? And I'll define it just for the subtour polytope, but it's true in general. I'm going to call it alpha sub of this polytope is the maximum possible value of the cost of the optimal solution over the cost of x over all instances and all x lying in this polytope. And why is this a useful concept? Well, we know that actually the optimal solution is feasible for this linear program. So the cost of x is certainly a lower bound for the cost of opt. And then if we know some bound on alpha of sub, we know that this is also at most alpha of sub times the cost of x. So the integrality gap gives us a really good way to sort of estimate the value of the optimal solution. Okay, so let's prove this result from Woolsey. Okay, I may struggle a bit to write below on this board, but I'll try. All right. I'm going to prove it's at most 3/2, and the proof is going to be pretty similar to Christofides' algorithm. So the first thing we're going to do is we're going to prove that the cost of the M is T. Minimum spanning tree is at most cost of X for any X in this polytope. All right. And now it turns out that without loss of generality, for X lying in this polytope, there exists an edge F such that X of F is equal to 1. And there are two ways you could do this. The first is that Boyd and Polyblank proved in the 90s that any vertex of this polytope has this property. So maybe that's enough for you. If not, you can also think about taking a vertex, kind of splitting it into two, and adding an edge of cost 0 between them. You can put kind of a value of 1 on that edge and split the value.
All that every X has this property you can make, you
Right.
can massage.
Right, so kind of like without loss of generality.
Generality.
Exactly, yeah, good. Yeah, so maybe it's enough to think about this extreme point fact. Okay, but actually, turns out this means that if I set z to be equal to xe for e not equal to f, and 0 for e to f, then z actually lies in the spanning tree polytope. And I'll define that now. So let's go to our polytope board. This was proved by Edmonds, 1970. But actually,
So PST does the convex hull for spanning.
exactly. So PST is actually the convex hull of the indicator vectors of integral spanning trees. And Edmonds proved that this polytope has a nice formulation. So the sum of the variables should be n minus 1. This is sort of obvious. This is true for trees. And then for every set S, the sum of the edges with both of their endpoints in S should be at most the size of S minus 1. And this is like saying that the graph should be acyclic, right? Because if I had a cycle, that would be a set with the size of S edges inside of it. And then, of course, this should be non-negative. Okay, so this is different than the other polytope because it has integral vertices. Okay, so let's say we prove this, then actually I claim it gives me this fact that the cost of the MST is the most the cost of X. And the reason is, maybe not so hard to see. Let's say I have the spanning tree polytope. Now I have this point Z, which lies inside of it. And I can write Z now using Carathéodore's theorem as the convex combination of some number of integral spanning trees. Right? So it's the average of some spanning trees. So definitely one of these spanning trees cost at most the cost of Z. So therefore, cost of the minimum spanning tree is at most the cost of X, which is most the cost of Z, because all I did was make one edge smaller, right? Okay, so let's prove this claim. Right. So the first inequality, or the first constraint of the spanning tree polytope should be pretty clear. Let's sum the ZE. Well, it's equal to the sum of the XE minus 1, right? Because I just made this edge F0. But what's the sum of the XE? Well, the degree sum is 2n. So half of that is the edge sum. Is n minus 1. So the first constraint, we're happy. Let's do the second constraint. So let's take any set S, and let's look at the sum of the edges that lie inside of S. Okay. So for sure, this is the sum of the XEs inside this set, because ZE is pointwise less than XE. But now, what is this equal to? So I'm going to do the degree sum for the edges, for the subgraph defined by S. So the degree of every vertex is 2. So we're going to begin with 2 of the size of S. But I'm counting the edges in the cut, right? So I should subtract those. So X delta of S just means the sum of the X weight on the edges in S. And now I've double counted, right? I've counted every edge in here twice. I should divide by 2. But now we know that X of delta of S, because we're in the subtour polytope, is at least 2. This thing is at most, 2S minus 2 over 2. And the second constraint is good as well. And of course, we're also non-negative.
So here you didn't use that you threw away that you decrease the C is smaller than.
That's right. The only
Because
place.
you don't know where F is.
Yeah. And the only place I actually use that is in the first constraint. Actually, there's many ways of kind of transforming X to get a point in the spanning tree polytope. Actually, in past work, often what people did was they just set Z to the n minus 1 over n times X. And this also works. Okay. So we proved this first thing. We know that the cost of the MST is the most the cost of X. Now let me do the second one. I'll keep Christofides for now because it's doing something similar. Okay, so the second thing is that the cost of this join is always at most half of the cost of X. And for this, I'm going to also use some polyhedral theory. So let's go to the polytope board. Okay, so this was proved by Edmonds and Johnson in 73. And they showed that the O-join polytope, where here O is going to be kind of a variable, right? It's the set of vertices that we want to have even degree. Sorry, odd degree. this is going to be equal to the set of constraints that y delta of s is at least 1 for all sets in which the intersection of s with O is odd.
What is G?
Sorry?
What is G or Y? What?
Oh yeah, this is y.
Now it's a variable.
Yeah, so I'm just sort of using my,
Again, on the edges, Y are called Y, yeah.
yeah, I'm using my kind of shorthand that I just sum up the y value of the edges in the cut. Yeah. So, okay, this constraint is easy, but this constraint, maybe when you first look at it, it's a bit unclear why this is the case. So let's say we have some cut separating an odd number of vertices on each side that we want to be in the join, right? But now, like, no matter what I do, maybe I can kind of join these two vertices. But now I'm going to have some path going across the cut in order for all my vertices to have odd parity, right? That's kind of why this constraint is here. And again, like the spanning tree polytope, this thing is actually technically it's the uphull of the set of integer O joints. So you can think of it as like some polyhedron where it's unbounded, but it's given by this uphull of the integral joints. And if you want to think about it like a polytope, you could just do this. If you want to add an upper bound of 1 on all the edges. Okay, and we're going to use kind of the same proof structure. We're going to show that x over 2 is in the O-join polytope for any set O. And actually, this should be pretty immediate, right? Because look at the subtor polytope. It says every cut should have at least 2 edges going across it. This says some cut should have 1 edge going across it, right? So clearly this is going to work out. And actually, I'm going to define another version of this, which some people who study TSP are going to be mad at me for this, but I'm going to call it the T-join polytope. And now T is going to be a spanning tree, T. And it's actually, I'm just going to define it as the O-join polytope, where O is the set of odd vertices of T. Okay, and now I can just translate this. And if you kind of translate this constraint, it says all sets for which the number of edges the tree has in that cut is odd. And it's not too hard to see this equivalence. Let's say I have a set S with an odd number of odd vertices. Now let's think of this graph where I take the complement of S and I contract it into a vertex. Now by the handshake lemma, this graph should have an even number of odd vertices. So if there's an odd number of odd vertices in here, it must be that this vertex was even. Sorry, it must be that this vertex was odd. But then that says that the cut was odd, right? Because the set of edges adjacent to this vertex in this graph is just the set of edges in the cut S. So that's why these constraints are actually the same. So I'm going to just rewrite this because I'm going to use this notation later. X over 2 is in the T-join polytope, where T is any tree. And in particular, we're going to take T to be the minimum spanning tree. Okay, so that's Woolsey's whole proof. I think it's a pretty beautiful, clean proof that just uses these kind of 2 integral polyhedra.
And it gives a difference, the house approximation in our program.
Exactly, yeah. Actually, it says Christofides is already 3 halves with respect to the LP. Yeah. Or yeah, I guess what you're also saying is you could just solve the LP and you estimate it. Yeah, exactly, yeah, good.
Now, that's generally what integrals get for one.
Right, right. Okay, so I'm gonna talk about very briefly some kind of folklore results maybe that happened around this time. So it's known that the integrality gap of the subfield polytope is at least 4/3. And the example here is it's called the envelope graph. And it looks like this. And part of the reason I'm drawing it is to kind of give you an example of a feasible point in the subfield polytope. So what is this? I'm just the dotted edges will have value 1/2, and the solid edges will have value 1. You can check that every vertex has degree 2, and every cut has at least 2 edges going across it. So this is a feasible point. Okay, and you can check that
Every vertex has degree what?
degree 2,
Weight 2.
weight 2, yeah,
Weight 2. It's not
Fraction,
degree. It's nothing to do.
fractional
with
degree. Sorry,
Well, yeah.
I'm gonna probably say fractional degree. So that's yeah, but good point.
Yeah, but when you mentioned degrees before, then even in these are
Right.
degrees, has nothing to do with the weight.
You're right. Yeah,
Yeah, so this is really weighted. Yeah,
weighted degree.
Every vertex has even weight.
That's right. Yeah, yeah. Okay, good. So the cost of x in this graph, actually, this graph is just going to be given by, so like I haven't really fully defined the instance yet. And the metric is just going to be the shortest path metric in this graph, which means that the weight of every edge is equal to the shortest path length between the two vertices. So that means that the cost of the LP here is just n, because all the edges I've used have weight 1. But it's not too hard to convince yourself that.
Why?
Yeah.
Why is that?
Because all the edges I've used have weight 1, and the sum of the XE is n.
So you are using, what is x? X is.
X is this vector where the dotted edges have value 1.
Okay, it's really the weight vector of the graph.
Yes, exactly.
Okay, fine.
So yeah, the LP is pretty cheap. It only has to pay n. It kind of acts like there's a Hamiltonian cycle here. But it's not too hard to convince yourself that the cost of opt, as these paths grow very long, is essentially 4/3 times n. Because what does opt have to do? Basically, it has to traverse the graph something like this. But now I have to get back to where I started. And to do that, I have to cross one of these paths again. So basically, I'm paying for 3 paths, and opt is paying for 4 paths. So that's how you get that the integrality gap is at least 4/3. Okay, and then there's this folklore conjecture, which has now become pretty well known. It's just called the 4/3 conjecture, and it's that, well, actually, maybe this lower bound is tight. In the first place I've seen this is a paper by Gomez in 95, but I think it was kind of talked about much earlier. Okay, and then the last folklore, it's not really a result, but I'm gonna call it the Christofides ++ algorithm. I'm gonna write it. Where did I write it? To keep it around. So, okay, I'll write it here for now. Well, I want history here. Okay. All right, I'll put it here. This way I can just put a ++ here. Okay. Okay, so first I solve my subtotal P. Now I'm going to write x minus this f edge of value 1 as a convex combination of integral spanning trees, right? So this is like the picture I drew before. We have this point in the spanning tree polytope, and I can write it using Theodoric's theorem as a convex combination of some trees. Okay, but this gives rise to some distributions mu over spanning trees.
Going to increase the font size again.
Okay, thanks, yeah. Good, and then my third step is kind of the thing you would like to do once you have a distribution over spanning trees. You'd like to sample one. Sample T from mu. And then do the same thing as Christofides. So, and add minimum costs. T join. So we know that, so now this is like a randomized approximation algorithm. And we know that the expected cost of this algorithm is certainly at most 3/2 times the cost of x, because the expected cost of the tree is equal to the cost of x minus this HF. And we know that for any tree, the cost of the T join is the most half the cost of x. So the hope now is, maybe now, since instead of just taking some arbitrary spanning tree, maybe, we have some nice property that, well, yes, x is in the spanning tree polytope, but it's also sort of on average equal to a TSP, at least a fractional TSP, right? So you might hope that this kind of does better. Unfortunately, it does not do better. So here's an example. Again, this is going to be a shortest path metric graph. And again, the dotted edges are equal to 1/2 and the solid edges are equal to 1. Okay, but now I'm going to forget about this f edge for the rest of the talk pretty much, so don't worry about that too much. I can now write it as a convex combination of two spanning trees. So I can write it like this. They both should have all these edges of weight 1. But now, like, one of them can take the internal cycle and one of them can take the external cycle. And so the cost of these spanning trees is the cost of x. But here, like, basically every vertex has odd degree, right? In both trees. Okay, I should have just drawn which vertices were even. Okay. Right, so there are n minus 2 odd vertices. But now the join is going to have to add at least n over 2 minus 1 edges to the graph, because every odd vertex should get at least one edge. So the cost of the join is essentially equal to n over 2. So the cost of the algorithm is now going to be 3/2 n. But in this case, actually it was Hamiltonian, right? So I can just take this. So opt was n. So even though it looked like a good idea, unfortunately, using this kind of convex combination of spanning trees, I didn't do better than 3/2. So for now, it seems like a good idea, but we're kind of a little bit unhappy with it.
That was a particularly bad in our combination.
Exactly. So that's the key idea to keep in mind is, okay, why did I pick this combination of spanning trees? Maybe that was a bad idea. And it took a long time to to sort of address Avi's point. Not the next thing I'm going to say, actually. The next very quick thing in history, 1993. Papa Dimitrio. Yanakakis. Show that metric TSP is APX. And in particular, they show that no approximation algorithm is going to do better than 1 plus 10 to the negative 6th. And this was improved over the years. And the current best bound is by Karpinski, Lampus, and Schmid.
Yeah, their result predates PCPs. Oh no, it was just
Sorry?
it's already PCPs existed.
Yeah, I think so. You would know better.
90, yeah.
Yeah.
1990.
Yeah. Good. So that's all I'm going to say about hardness, but this is the best we know. So very far from yes.
Is that 123 over 122? Is that what the number is?
Yes, that's right. Also means I should write bigger. So thanks. Okay, so now the next thing is going to kind of address Avi's point about the combination in Christofides++. Okay, so in 2011, Ovescaron, Severi, and Singh show that it's the max entropy algorithm is a 3/2 minus epsilon approximation for graphic TSP. And graphic TSP just means shortest path metrics. So all the examples I've been giving you are examples of graphic TSP.
We're on the weights. The metric, it's a weighted graph and
So the graph is unweighted.
unweighted. Okay.
That's what the graphic part means. And then, yeah, if you allow weighted graphs, then actually it's a completely general
Okay.
version of the
What
problem.
was some paper of Vishnoi for some.
Oh yeah, so this is so when was max entropy actually introduced? So in 2010, sorry, I looked it up too. Asadpour, Gomez, Madrai, Ovescaron, and Severi introduced the max entropy algorithm. And they actually use it for ATSP, the asymmetric traveling salesman problem, where the metric can be asymmetric.
What does it mean, we have minus epsilon approximation? Like,
Yeah, so they found an absolute constant. It was like, I'm not sure they actually computed it. I think it's supposed to be something like 10 to the negative 60, such that this algorithm, which I'm about to tell you about, is at worst a 3/2 minus epsilon approximation. And actually, I should say this is randomized. So they just prove the expected cost of the algorithm is 3/2 minus epsilon.
Do any of the hardness results you stated work for graphic TSP or no?
No, yeah, not that I know of. I think the hardness results are for 1-2 TSP, where every pair of vertices has either distance 1 or 2. Is that? You might be able to actually, maybe that might be graphic in some sense. I should be careful when I say it's not graphic. I guess you could put an edge for all the pairs at distance 1, and then that. Yeah, I'm not sure. You might have to.
You can maybe put a point at
Yeah.
the midpoint of the edge and make it
Subdivide.
two edges of distance one?
Then you have to use the edge because you have to hit that vertex in the middle.
I mean, you have to cross through it, right? You can't like go back. Oh, okay.
Yeah, like you're forcing yourself to use that edge there. So, yeah, I'm not sure. It's a good question. Yeah. Okay.
So actually going back to
Mhm.
Avi's question,
Mhm.
the Vishnoy paper, the permanent approach to TSP, is that analyzing the same algorithm or is that?
No, that's a totally different idea. Yeah. But you could say there's a relationship because sort of sampling and matchings instead of trees, but
I see.
no. Okay, good. So actually, what is this algorithm? So it's Christofides ++, except I'm going to change step 2. So change this. Max entropy algorithm. And instead of step 2, where I just did some arbitrary convex combination using like Carr-Theodori or something, I'm actually gonna let mu be the distribution of maximal entropy. Maximum. Subject to this constraint that in expectation it's equal to this point x minus f. That's the algorithm, and it turns out that beats Christofides, at least so far we know this for the graphic case.
And you want to argue that we can find such a.
Right, so yeah, so now this looks a bit sketchy, right? So why can I find this thing? And maybe the most natural thing you'd start with is some convex program where I want to maximize, so I'm going to create a variable PT for every spanning tree of the graph. And now I just want to maximize my entropy, right? So subject to the constraint that I'm a convex combination of X, subject to this constraint that when I sum over the trees containing a particular edge E, this is actually equal to XE, and actually I'll say ZE, because Z is going to be some point in the spanning tree polytope, right? So this is like sort of what you try, but it looks a little scary because, as we all know, like trees may have exponentially, or graphs may have exponentially many spanning trees. So this program we can't really solve it directly. But it turns out that since there's only polynomially many constraints, this can be solved. We take the Lagrangian dual of this. And actually first let me just change this max to a min and flip the sign. Okay. Now I'm going to take the Lagrangian dual. This is going to be the max over delta, the min over some PT log PT. And now I have to kind of encode my constraints in the objective function. So I'm going to ask that this should be over positive PTs. I'm going to ask that yeah, these constraints are met. So ZE minus sum of PT is encoded here.
So delta E is every variable has a penalty. Value.
Exactly, yeah. So I'm creating a penalty
For
for all of these constraints, all these edges. Okay, but now if you sort of stare at this for a second, you notice that once I fix delta, this actually becomes very simple. So this is just for a fixed delta. Just going to sum over PT log PT. And then like once I fix a tree, what am I going to get for that tree? I'm going to get a negative PT Z delta E for every edge in the tree, right? So this is sort of a contribution for each PT independently. And then I'm going to get this extra term that doesn't really depend on anything I do. It's just delta EZ, right? Okay, but
Sorry, what is it? Oh, you just, this is a thing without the mark that.
yes, so I'm just rewriting, I'm saying if the delta is, I mean, I'm just rewriting this expression actually. Yeah. So I haven't done much so far.
So what's the summation at the end of over what is?
This is over all edges. Okay. Can you hear? Give you time to stare at it a little bit longer. So now, kind of as I said, suppose that delta is fixed and you want to minimize this expression for PT. And you can now notice that it's just the sum over a bunch of convex functions that have no relationships with one another, right? So it's just independent in each PT. So I can optimize them individually. So let's do that. So I just have these functions. Basically, yeah, PT log PT minus PT. Now I want to take the derivative and put it to 0. So let's take the derivative with respect to PT. This is going to be.
Start the sum to 1 though.
Sorry?
They start the sum to 1.
The PTs?
Yeah.
Yeah. So it turns out that's going to be kind of an implicit constraint given by the deltas. But I may be a little bit fast and loose here. But there is really no constraint in this convex program that says that so far. So this is going to be, it's going to be log of PT plus 1. I'm just taking the derivative, and then minus sum of delta E for the edges in the tree. Okay. Let's make the 0. And now solving for PT, I can just set PT equal to E to the sum of delta E minus 1. And now if I set, sorry?
It's the next part.
Yes, this is the next one. Yes. So now if I set lambda E for all edges to be equal to E to the delta E minus 1 over n minus 1. Oh yeah, this is hard to read, is that?
Now there are two E's and one of them is a known constant.
Yes, okay, I see. Got it. Okay, good. So if I set lambda E to be this thing, then actually PT for all of the trees is just equal to the product of the lambda E's for the edges in its edge set. So what this says is that
You should expect for maximum previously.
yeah, I think you should expect this. But what it says is that, you know, if I actually have a maximum entropy distribution, it has this structure where the probability of each tree is just proportional to the product of these numbers. Okay, good.
This particular evaluation of the matching to the polynomial. Right, I mean, general things that, this one PT and the sum of them is the sum of all spanning trees.
Mhm.
Is Yeah, yeah, I don't know, so I don't know who something you do, but like if you want to last week talk, and many of these statistical physics problems, you get with parameters on the edges or vertices of a system, and you sum over, all configurations. Here the configurations are trees, the weights of the parameters are some constant. You determine them for this optimization.
Right.
In general, the partition function of the system is the sum over all configurations of such product.
Yeah.
Anyway, so they appear there in enumeration problems.
Yes.
In general.
Yeah.
And here to get the max entropy distribution, I guess you need to divide. It's not PT, it's actually, if you want probabilities, you have to divide it by the partition function, right? If you want this to be a probability distribution, you have to divide it by the sum over all trees.
Right.
So,
Yeah, we can write, yeah, good.
yeah.
Yeah, thanks. Yeah, actually, this is also the good answer to this question. Normalization, making sure everything sums to one. Yeah. Okay, so now that we know that there's kind of a compact description, polynomial size for max entropy distributions, right? We just have these vectors, lambda. We can hope to actually find them in polynomial time. And that's what was proved in this 2010 paper. Is given a point in the spanning tree polytope and some epsilon, which is going to be our error, we can find lambda in time polynomial in n and log 1 over epsilon, such that up to this error lambda, essentially this distribution has marginal z. In other words, the probability that an edge is in the tree, we sample from this mu lambda distribution, which just means that this is for every tree. It's going to be a most 1 plus epsilon times ze for all edges. And we can take epsilon to be like exponentially small in n, right? So we can kind of just ignore this and just think about it as an inequality.
But still, I will still bother you about this. I mean, these are spanning trees are a particular set of a graph, a particularly set system. Matching of a graph is another set system. And suppose you want a maximal entropy distribution of these sets, given some linear constraints. And maximum entropy, you think of something that would be independent. And I think in general, there will always be parameters lambda e. So that it will be a product that's as independent as you can, so that the lambda e satisfies the linear constraints.
Yeah, and so this theorem was generalized by Singh and Bishnoi, which said that I'll just say it's like given any family of discrete objects, as long as you can evaluate and approximately count the partition function, should be like summing over those objects. So you have some family M. As long as we can evaluate this, approximately in polynomial time, then we can also compute the max entropy distribution. And actually, the reason we can do this for spanning trees is the matrix tree theorem. Okay.
Nathan?
Yeah.
We jumped into calculating this. My question probably speaks of my inexperience in the field.
Okay.
But why is this a good idea? Like, why are we doing? Why of all the things are we looking at like maximum entropy?
Great question. Yeah. I think no one. It turns out it works, and maybe that's the best answer. It works to be 3S, but I think
anybody has any good idea.
but I guess, okay, so we want to avoid situations like this into where we decompose a point into some very adversarial spanning trees. So we sort of want to say like, you know, I don't want to influence the way in which we choose the spanning trees. I want it to be as random as possible. And that's exactly what this max entropy idea is. It's saying I kind of want to avoid putting any bias on how these trees should look.
You really want the spanning trees to have a few addresses. That's what you really want. And where will you look for them? Or let's look at all of them.
Right, let's look at all of them.
I don't know that there's more intuition.
I don't think so, yeah.
But max entropy works in a lot of other places.
Yeah.
It's a principle that works in lots of different areas, so.
Yeah, but that doesn't explain why.
Yeah.
Maybe there's
Yeah.
a different distribution.
It makes sense, I think, in other places.
So you don't get stuck maybe in bad places, but maybe there's a better way.
So just to make it more concrete,
Hmm?
there's a different distribution you could try, which is like the uniformly random distribution. That's not the same here.
No,
Oh, so that would present an issue potentially because we want to make sure the expected cost of the tree is equal to the cost of X. And if you just take a uniformly random spanning tree, it could be very expensive. If you're working in the graphic case, maybe you could try something there where all the edges have the same weight. But in general, that would be a problem. It's important to have this constraint that
It is like being as uniform as possible.
Subject to the constraint.
exactly,
yeah, but that's what it is.
That's what it is. Yeah.
It's independent. But there's another, it's not clear that you need to compute this, right? You can sample from it. It may be good enough. I mean, if you could, suppose you had a Markov chain that samples from a max entropy distribution. Couldn't you use it in an algorithm?
Yeah, that's
For sure, it would be the same. Yeah, you don't have to solve the optimization.
yeah, and actually, they proved that while you can use this convex programming framework to get the error of log 1 over epsilon, they also showed that a multiplicative weight update algorithm using these lambdas works as well. So you sort of start with all of the lambda e's equal to 1, and while an edge is sort of too likely to be in the tree, I just slightly decrease the lambda, and they show that this converges in polynomial time, but now it's polynomial 1 over epsilon, not log 1 over epsilon. But basically, this is also good enough. Okay. So let's keep moving forward in time a little bit. In 2021. Yes. Sorry. With Anna Carlin and China Viscaran, we proved that max entropy is a 3/2 minus epsilon randomized approximation. And epsilon was the Planck constant over 100. I won't tell you what that is. And then in 2022, we proved that the integrality gap of the subtour polytope is also amongst this number. In 23, we proved that there's a deterministic three-halves minus epsilon approximation.
Is epsilon changing in these results?
These are all the same. Okay, yeah. And then pretty recently with Jin and Williamson, we proved that max entropy is no better than 1.375, which says that it does not resolve the 4/3 conjecture. Too bad. Okay, and then the final development with Gurvitz and Week we improved epsilon to about the Planck constant. So yeah, we got rid of this 100, but that wasn't the main point. We kind of like sharpened many of the probabilistic lemmas in the paper, cleans things up a bit using polynomial capacity. Okay, so this is let's see what time it is. Yeah, actually, now that I've kind of presented you with all the evidence, I wanted to ask Avi if he has a conjecture about like what the approximation ratio for max entropy is.
No, I spent time trying to prove, say, after I was a PhD student, which was.
Just pick a number between
Most of
1.
them were born, and then I left.
No, just pick a number between 1.375. You can call it Avi's conjecture. And,
Yeah, you can maybe formish it too.
okay, we'll take a break now for 5 minutes, and we'll let Avi think. And then when we come back, I'll give you some intuition for Avi's conjecture.
Right, yeah. Yeah, my conjecture is that this is like,
Okay,
at least I want to see, and I'm giving intuition to a false conjecture.
good.
Of course, conjecture, it doesn't believe.
Yeah, okay, so Avi thinks it's 1.375. And now let's give some intuition for this conjecture. And the first thing is going to be to prove that definitely it's not lower than this.
Let me ask you just a funny
Yeah.
question. Are there any like digits afterwards, or it's like 1.3?
So it's exactly this, yeah. I mean, technically there's a little of 1.
That's 11/8 or
Mhm. Okay, so here's the graph. Think of it as a very, very large, and it's going to be a circle. It's connected to the bottom. And again, it's like it's half integral instance. So the edges are dotted are 1/2, and the other edges are 1. And it's also the shortest point of the tree. So this also says that even in this graphic TSP regime, it's no better than 1.375. So I think is a bit surprising because there's a paper by Williamson and Genova that kind of simulates the performance of max entropy. And empirically on graphic instances, it does like extremely well, like 1.01 or better on and kind of anything they tried. So it's kind of interesting that the counterexample we had is graphic. I'm just going to kind of sketch this proof for you. My first claim is that actually max entropy on this instance is very simple. And does anyone see sort of why it should be easy to find the max entropy distribution on this graph? Not so obvious, but
It's symmetric, so at least we know that on all the solid edges it's the same lambda.
that's true. Yeah.
And on the dotted, maybe it's different.
Circle is here. Let's look at these edges E and F. What do we know about E and F? XE plus XF is 1. We can't choose both of them, right? Okay. So any spanning tree has at most one of them. Okay, so I have 2 random variables. This expectation is 1, and I can always use at most one of them.
so sorry, wait, why can you lose?
Like, oh yeah, because I'm always going to take these edges that are set to 1
Oh,
every spanning tree, because I'm going to do a convex combination of x.
Yep.
But now, like, I can't take E and F because I would get a cycle. So I have 2 random variables. Their expectation is 1, but I can only ever take one of them. So that says I should always take exactly one of them. Okay.
So what's X?
What is x? X is it's 1/2 on the dotted edges.
Okay.
It's 1 on that. Yeah. So it says we always have for each of these kind of squares, we always have exactly one of these 2 edges, E or F. and so on. Okay. But now this says that actually each of these squares is going to be some connected component of the tree. So now let's look at these edges like G and H. They're in the same position. They have expectation 1 when you sum them, but you can only take one of them because I'm going to have a connected component here and a connected component here. So if I took both, I would get a cycle. So I always have kind of G or H. Okay, and then the last thing to notice is that actually any way that I take E or F, G or H, E prime F prime, G prime H prime is going to give me a spanning tree. So what's the max entropy distribution? I just make each choice independently to maximize entropy. This example is nice because unlike kind of many instances, it's like very, very clear what max entropy is doing. Let me zoom in on one of these squares. Really, there are only two things that can happen. Either I get the same edge coming from these pairs of dotted edges, and I get some edge inside, or I get different edges and some edge inside. Okay, but now let's look at the odd degree vertices just in these pieces. So here, this vertex is odd and this vertex is odd. And here, this vertex is odd and this vertex is odd. And this is really all that can happen up to symmetry. And now it's actually not so hard to prove that as the number of vertices goes to infinity, the best you can do in the matching, or the join, T-join, is to match or join these edges within each of the squares. This is basically the best you can do. Okay, but now I have n over 4 of these squares. So what's the expected cost of the join? I have n over 4 squares. And probably 1/2 is going to cost me 2. And probably 1/2 is going to cost me 1. So exactly 3/8 n. And that's basically the whole proof. So it's a very short paper. And we tried sort of various things like modifications on this cycle and sort of simulated it computationally, and we couldn't find anything worse. So, so far, this is the best lower bound we have.
Sorry, why the join could not happen between the adjacent?
Right. So that's a great point. Is that you might say, hey, if it looks like this, maybe you should have. And I had an odd vertex here. Maybe you should have joined these two vertices instead. And that's actually true, but essentially there's only two matchings in the whole graph. I either do the matching inside the squares, or I do the matching inside these squares. And you can prove that actually one of those two matchings is optimal. And the analysis is really the same as this. So then you analyze both of these joins at the same time, and kind of with high probability, they're both going to cost 3/8 n. But yeah, that's a good question. Okay. So that's the lower bound. Now, I'm going to give you, I think, my favorite piece of evidence for obvious conjecture. And it's going to take me a bit to prove, but I think it really gives a lot of the key ideas of the analysis. So I guess worth the time investment. But here's the lemma. So let mu be a lambda uniform distribution with marginals x in the subgroup polytope.
So what's this? Lambda?
lambda uniform. So it's the max entropy distribution where you have these lambdas that give you the probability of the tree. Should maybe write this somewhere. So you have a lambda vector, and then the probability of the tree is going to be equal to the product of the lambdas in its edge set over this for all trees. Okay, that's illegible, but yeah. Hopefully you get the idea.
Anybody look at your, I mean, the linear program giving you x feasible points
Mhm.
can give you all sorts of x's. In fact, maybe there are many solutions.
Mhm.
Even looking at them before finding the max entropy distribution for that x. Because here x is clearly lousy, right? I mean, it wastes a lot of things. I mean, the graph is Hamiltonian.
Mhm.
It could use only one of these edges, not half of course.
Right.
Right. So maybe there are more x's solving the linear program that are better before you apply.
Yeah, I guess
I don't know if anybody tried.
the thing you have to be careful about is I guess there could be a unique x, right? For any
It could be,
for any
but
weight
I don't
function.
know if maybe,
And adversarially, like there should always be a unique x, I guess. You could just slightly tweak the weights that it's unique. But I think like
But
I
what
think
do you mean unique? It means that
the minimizer is unique. We're gonna solve this LP to get
yeah,
the
so the
minimum cost.
minimizer, I see, the minimizer would be unique.
But I think there's a good question, which is like, you are actually okay if the LP costs a little bit more than
you
have some, exactly. So
There's one over the Planck constant.
yeah, exactly. So you could ask like maybe sort of there's some small ball you can move X in and that might give you something better. I think that's, I don't know anyone who's looked at that, but I am currently looking a little bit at like ways to strengthen X, maybe with Strauss atoms or something like that. It's another direction you could go, but yeah. Okay, so here's this lemma, is let mu be a lambda uniform distribution with marginals X. Then for all vertices, probability that just say V has even degree in T is at least 1/2 1 minus e to the -2, which is about 0.43. Let me know if this makes you update your constant. Yeah. Okay, so to prove this. And basically there are going to be 3 parts to this proof. So first, we're going to view this distribution mu as a polynomial. Okay, and in particular, it's going to be the generating polynomial of the distribution. And here I'm abusing notation a bit, and n is the number of edges. These are sort of edge variables. And this is going to be equal to the sum over all trees, probability of the tree, times the product of the ZE, the edges in its edge set. Actually, you can kind of notice that you can also just do this. Right. And if you'd like, this is also equal to the determinant of this matrix. This is a nice polynomial with like a compact description. I'm not going to talk about this too much, but
What did you write them? What is before the ZE?
this is the Laplacian of the edge E. I'm not going to go into it yet, but in case you are familiar with the matrix tree theorem and this stuff. Okay, and then the second thing is we're going to study the roots of this polynomial. It turns out we do know a lot about the roots of G of mu, so it's proved by Ortea, Brandon, and Liggett, 2009. That G of mu is a real stable polynomial. So what does this mean? So a polynomial P with real coefficients is real stable. So the real part just means it has real coefficients. If whenever I plug in values with all positive imaginary group, this polynomial is not zero. So its zeros avoid the upper half complex plane.
N equals 1, it just means that all the roots are real.
Yeah, good. So it's some kind of generalization of real rootedness. And actually, they also proved some other things. This paper, so they proved some closure properties of real stable polynomials. So let's say we start with a real stable polynomial P. They proved that if I replace any of the values with a real number, then this polynomial is also real stable. And this is not too hard to see, actually. So first notice that P with A plus I over K, this is definitely real stable because I plugged in something for K positive. I plugged in something with a positive imaginary value in the first component. And so if I had some zero in the upper half plane here, I could just plug in Z2 through Zn and A plus I over K, and I'll get a zero of the original polynomial. So this is definitely real stable. But now if I take the limit as K goes to infinity, this is exactly the P that I run. And now you apply Hurwitz's theorem to tell you that actually the corollary of Hurwitz's theorem is that the limit of a real stable polynomial is also real stable. That gives you the first result.
This was not known earlier. And this closure properties.
The closure properties, yeah, I would say they're not really so new, but the new thing was sort of studying these distributions as polynomials. Yeah. Yeah, I don't know when, I should know, but I don't know when this was first proved in general. The second thing,
Even Rubik in this, command paper uses the closure properties. I'm not sure which, but some of them.
yeah, sorry. So this is,
These were known to mathematicians earlier.
yeah, great point. So this work is more about using real stability to study distributions, and this is definitely these things are not so hard. So yeah. So it turns out also if I make any two variables the same in this polynomial, that's also real stable. And that's pretty intuitive, right? Because like if there was a root here in the upper half plane, I could just plug in the same values again for the original polynomial. So this is also real stable. Okay, so now we know some stuff about the roots. The third ingredient is to use the structure of the roots to learn something about our distribution mu. Right? So let's try to start proving this parity.
Maybe you want to say something about even the case of one variable. We know if that the polynomial is really rooted, then as a distribution, it's.
I'll prove that.
You
Yeah,
are.
I'll say this. Yeah. Actually, so first I'll say maybe this was sort of a topic of this paper by Borchea, Brandon, Liggett, and they kind of characterized, say if G mu is real stable, mu is strongly Rowley. And they proved many nice things about strongly Rayleigh using these kinds of closure properties. For example, these distributions are negatively correlated, and they even have the stronger negative association property. And these closure properties, as I'll talk about right now, correspond to sort of natural operations you would do on a probability distribution.
So you didn't define strongly Rayleigh, but
This is the definition of strongly Rayleigh.
how many
Yeah.
people heard about negatively associated, when you mentioned this too, negatively associated random variable? So for example, Chernoff, we have very few. Chernoff bounds, which hold for independent random variables, hold for much more general
Right.
distributions called negatively associated, like a negative correlation between the variables and the solution. Anyway,
Yeah. So these are really nice distributions, and lambda uniform distributions are an example of them. Okay, so now let's try to prove our claim. We'll get stuck, but let's start. So let's zoom in on a vertex here, and let's say the variables corresponding to these edges are z1, z2, up to zk. So we begin with our sort of full generating polynomial. And now what I'm going to do is replace all the variables after zk with just the value 1. And by our closure properties, this is still a real stable polynomial. And it's just a polynomial in k variables now. The second thing I'm going to do is I'm going to make all of the variables the same. By the second closure property, this is again real stable. And as Avi said, this is now just a univariate real stable polynomial, which is a real rooted polynomial. And that's just because for real polynomials, their roots come in conjugate pairs. So if I have a root down here, I'm also going to have a root up here in the upper half plane. Okay, so this is kind of nice. Now we know that this distribution telling us about the number of edges adjacent to the vertex V is sort of associated with this real rooted polynomial. I probably, yeah, well.
we are
Sorry?
we are still going for showing that you have lots of even degree, a few odd degree.
Yeah, still going for this.
Like not for shaving the cost of the matching or join. Yeah.
Yeah, unfortunately, I should erase this. Okay. Good. So now we have this real stable polynomial telling us about the degree of this vertex. Now we're going to use a theorem of Edry from 53, which is let P be a polynomial with real positive coefficients. We make it P of Z. Then there exist Bernoulli random variables, D1 and D, where D is the degree of this polynomial, such that I can actually rewrite P of Z with like AI, Z to the I. This is also equal to the probability that the sum of the Bernoullis is equal to I times x to the I. In other words, the coefficients of this polynomial are fully described by these independent Bernoulli random variables.
So you are shooting for semantic concentration like that?
Yeah, we'll see. You'll see shortly. Yeah. Okay, so let's prove this quickly. Actually, a very easy proof. Okay, so I can write P of Z as some constant, actually A of D, times the products of the roots. Okay, and we know here that C is positive, And all the lambda i's, the roots, all the roots are negative because the polynomial has positive coefficients. Okay. I'm also going to assume that P of 1 is 1. And if not, you can rescale. But for us, it's going to be the case that P of 1 is 1 because we have a probability distribution. So the sum of the coefficients is just 1. So that actually tells me what C is. Because if I plug in 1, this is going to be 1 is equal to C times the product of these things. So C is going to be 1 over the product of 1 plus lambda I. So I can rewrite this as Z over 1 plus lambda I plus lambda I over 1 plus lambda I. And you might already kind of see where this is going. Let me rewrite it one more time. This is also equal to product of these terms. And now if I set Pi to be equal to 1 plus 1 over lambda I, let me rewrite this one more time. This is just equal to Z times Pi plus 1 minus Pi. So Pi's here are going to be the success probabilities of my Bernoullis. And now the coefficient of Z to the I is just going to be the probability that I get I successes this product, right? That's actually the whole proof of this theorem.
So X should be Z in the statement? Or
This is a Z. It's not relevant, but
the last X?
oh, sorry, yes. Thanks.
So were you assuming that P is real rooted?
Yes. Also, thank you. That's how I got this expansion.
It's important that the Bernoullis you get are independent.
Yes, yeah. Otherwise, I think you could do some weird stuff. Yeah, but they're going to be independent. Okay, so now thinking back to my problem, I know that actually this distribution is identical to the success probabilities of some number of Bernoullis. So the problem already looks a lot easier. And you could probably just sort of like dive in and figure out this number already. But I'm going to make it even easier for us. This is a theorem from Hofting from 56, which I really like this theorem, so that's why I'm saying it. So let B1 through BD be independent Bernoullis. Then for any function G, from the integer to the reals, then any function G is minimized or maximized when all of the success probabilities, so you're going to have success probabilities P1 to PD, when all the success probabilities are in the set 0, 1, P for some fixed P. So some can be 0, some can be 1, and the rest are all equal. Sorry, and I also forgot. What is minimized or maximized? It's not the function itself. It's the expected value of this function over the sum of the pi's. So any function G, this is minimized or maximized. And yeah, I think this is so cool because it doesn't depend on the function. It's like any function I want.
What is P in the statement?
P is just going to be some fixed
Of the PI.
constant. Yeah, so either, another way to say it is that all the PIs are either 0, 1, or the same.
Oh, okay.
Okay, so now that we have this nice tool, we can go back to thinking about our problem. So let's let n be the number. Actually, sorry, first I want to say that let's let B1, BD be the independent Bernoullis in our distribution. And let's say P1 is at least P2, so on up to P of D. I claim that for our distribution, P1 is equal to 1. Does anyone see why this is true? So one of the Bernoullis, if I'm looking at the degree of a vertex, has to be 1.
Because it's a span, well, one of them is in the Spanish tree.
Yeah, so these don't correspond to edges, these Bernoullis, but we have to have that the coefficient of z to the 0, the constant term is not 0, because sorry, the constant term is there is no constant term in this polynomial, because the probability that I have one edge adjacent, 0 edges adjacent to a vertex is 0. And the only way I can do that in this independent Bernoulli's distribution is if one of them is equal to 1. If they're all less than 1, there'd be some chance that I got 0 of them. Okay, so one of these PIs is equal to 1. And then the rest, the expectation of the number of edges adjacent to this vertex was 2. So the sum of the rest of the PIs should be 1. Okay, so now let's just apply Hofting. Let's say n is the number of non-zero Bernoullis, in the sense that their PIs are non-zero, in P2 through PT. Then now I can just like directly compute probability that this vertex is even. Right, so the probability is even. It's going to be the probability that the sum of these BIs from 2 to D is odd, because the first one is always going to be equal to 1. Right, and this is just summation out of n choose k odd, p to the k, 1 minus p to the n minus k. I'm sure everyone knows how to compute this now, but there's a kind of cube trick we can use. So say 1 is equal to p plus 1 minus p is equal to this. Now let's do negative p, 1 minus 2p to the n, sorry. Now let's subtract these two equations. Oh, sorry. Thanks. Now we subtract these equations, I'm going to get 1 minus 2p to the n. Now the terms where k is even are going to cancel. So I'm just going to get sum over the odd terms. And I get them twice, right? Because I appear once here and once here. Okay. N minus k. And this thing is exactly probability that the sum was odd. Okay, and so put the 1/2 over here. Get rid of the 2. And what is p? Well, it's just 1 over n, 1 over the number of non-zeros. So this is, in the worst case, n is going to go to infinity, in which case this is exactly the bound that we have up here, 1/2 times 1 minus e to the negative 2. Yeah, okay, so let's see how much time I have. Yeah, all right. So this is a sort of a nice piece of evidence for the conjecture.
It just says that you may be able to save a quarter almost of, from Christofides. Only half the vertices are on average are odd.
Yeah.
And if you shortcut from you would get like 1 and a quarter.
Yeah, so maybe you could guess like a bit more than 5/4, yeah. However, it turns out that this fact alone is not enough. So there are distributions over spanning trees where even like half the vertices are going to be even, and you don't beat 3/2. So it's good, but it's kind of not enough. I don't have too much time, but I'm going to tell you kind of now a very brief proof sketch of how we actually prove 3/2 minus epsilon. So here's the main theorem we proved. Is that for a lambda uniform distribution with marginals x in the subtour polytope, there exists a function y from the set of all spanning trees to vectors over the edges such that, okay, first, y of t is in the t-joint polytope of t with probability 1. And then second, for all edges, the expected value of ye, where ye is like a random variable over the choice of the tree t, is the most 1/2 minus epsilon times x of e. This is our sort of main theorem. And we can see easily that it implies the main result. Because kind of notice these three things. So one, the cost of the joint the algorithm actually uses is at most the cost of y for any tree t, because this is going to be some point in the t-joint polytope, so the cheapest t-joint costs at most y. So therefore, the expected cost of the join is the most the expected cost y. But now we can just use the second thing. Say that this is at most sum of CE xe times 1/2 minus epsilon, where we just use linearity of expectation in the second fact. This says that since the cost of the tree is equal to the cost of x, this is going to be at most the cost of x plus 1/2 minus epsilon times the cost of x. This is going to be our approach. Okay, and it turns out that what's going to be very relevant to proving this theorem is the small cuts of the support graph of x. So let's look at some example LP solution. Now I want to look at all the cuts S, where x of delta of S at most 2 plus eta for some very small constant eta. So think of eta as like 10 to the negative 10. So in this graph, what are the small cuts? I'm going to get all of these. These have value 2. I'm also going to get all the vertices. And I'm also going to get this collection of cuts that kind of cross one another. Okay. So this is the set S eta small cuts. And now what my approach is going to be is I'm going to start at y of t equal to x over 2. This is kind of going to be my starting point. And now remember this T-joint polytope. It has a constraint for every cut in which the tree has an odd number of edges. I'm going to kind of visualize all the constraints, no matter the parity of the tree, here. So we have some that are kind of very close to being broken, and we have some that are kind of like a little bit farther away. This is a very rough picture, but this is kind of what's going on. And actually, the set of small cuts correspond to the set of constraints that are really stopping me from decreasing my objective function when I kind of start at this x over 2. So what I'm actually going to promise is that y is kind of going to stay inside a small ball close to x over 2, which says that, while there are exponentially many cuts to worry about, I'm only going to care about the constraints that are very close to being violated already. And that corresponds to the small cuts of the graph. And one nice thing is that the size of S eta, the most n choose 2. So we went from an exponential number of constraints to just a polynomial number of constraints.
The non-trivial fact, but
Sorry?
I mean, it's not a trivial fact.
Yeah.
The number of small cuts
Not trivial.
or but for those Cargill or
Right.
earlier things. Yeah.
Yeah,
But by the way, there can be the point can actually lie on one of these.
yeah, for sure.
Yeah, it's not a way. It can-
Yeah, I should probably draw one. Yeah. Okay, good. And what we're going to use now is, okay, for example, like these small cuts are the vertices of the graph. But now every vertex is going to disappear from the set of constraints with probability like 0.44. So you can think of this sampling a random tree as this like random process where I come in, I delete some of these constraints, and then I tell you, okay, now that you've deleted these constraints, can I actually decrease the value of the objective function? Clearly, if I deleted like all of the blue constraints, I could just decrease to sort of the edge of this ball, but it's a little more complicated than that, right? I'm only going to be missing around half of my constraints. But this is the overall proof strategy. And what we then do is we partition S eta into the set of cuts that are not crossed at all. So these blue sets plus the vertices, where two sets cross if all 4 of these regions of the graph are non-empty. And then we're also going to get this kind of crossing component of cuts, which is equal to all of these red sets here. And
Can you repeat the definition of each set?
yeah, so H sub eta is the set of cuts, the small cuts in this graph that are not crossed by any other small cut.
But what do you mean? This is just one graph. You want it to work for all.
Yeah, so you look at the set of small cuts in your support graph.
Yeah.
And you take in H eta every small set that's not crossed by another small set.
Okay.
And C of eta is all the other
Yeah.
small sets, yeah. And then we're going to prove 2 theorems. So first one is that there exists a function yc in the set of trees, vectors on the edges, such that for all cuts that are crossing in C eta, should I make this S? If S appears in this T-joint polytope, this is odd, then the value of this on the cut is at least eta over 4. The second thing we're going to prove is that for all edges, the expected value of yc of E is very small. The most order of eta squared times xe. This vector, we can think of it as kind of like boosting the value of the odd crossing cuts in the T-joint while remaining quite cheap. Okay, 7. In the second theorem, we're going to prove that there exists a YH. And this one is allowed to actually take negative values, such that for all cuts that are not crossed, if S is odd, so if the number of edges it has in the tree is odd, oh, this should have been T, sorry. Then the value of this vector on delta of S is non-negative. So in other words, this vector is not going to break any of the constraints in the hierarchy. The second thing is going to be that for all edges, the expected value of YE is going to be negative omega of eta times XE. And finally, we're going to have the constraint that we kind of stay inside this small ball. So we're not going to be too negative. So all of the time, YE of H is going to be at least negative eta over 8 times XE. And now, my final function is going to be equal to my starting point, x over 2, plus YC plus YH. So I'm going to kind of start at x over 2, and then sort of wiggle a little bit so that I reduce my objective function without breaking any of the important constraints. So let's see why these two technical theorems actually imply this theorem over here. So the first claim is that the expected value of YE is going to be at most f minus epsilon XE. This one is pretty clear, right? Because YE is going to be 1/2 XE. This is the expected value. Starts off at 1/2 XE. And this thing is going to give me a small positive term of order eta squared XE. But then this is going to give me a negative term that's omega of eta. Okay, so for some choice of eta, which I get to choose, this is going to be 1/2 minus epsilon. Okay, and then the second claim is that this y is actually in the T-joint polytope. So to do that, I'm going to check.
Just because what is bigger than an X.
Basically, so you need a little, yeah, okay, so just so everyone's on the same page, even though maybe Avi's already seen it. Let's look over all odd cuts S. Let's look at the value of YC, YH, and finally Y. So let's look at first some set S, which is going to be in H of eta. Okay, so YC, I'm just going to use that it's non-negative. So at least 0. Y of H, whenever a cut in H of eta is odd, we have that it's non-zero, or non-negative. And then Y is, of course, going to be at least one. Because I've taken x over 2, and I've just added these two things. Okay, so let's now take something in C of eta. Here, we know that if S and C of eta is odd, we're going to get this boost from YC. So this is going to be at least eta over 4. And here, we're going to use that Y of H is never too negative. So this is going to be at least negative eta over 8, x of delta of S. If I put these things together, I'm going to get 1/2 minus eta over 8, x of delta of S plus eta over 4. And so you can see this is minimized when x of delta of S is 2. So this sum is going to be at least 1. And finally, what happens when we have a cut that's not small, it's kind of outside of this ball? This is again going to be non-negative. This is again going to be at least eta over 8. And now here I have the same thing, because I don't have this additive term. But now what I get to use is that this thing is not a small cut, so it's at least of size 2 plus eta. So this is at least 1. So yeah, this is the structure of the proof. I think we're pretty much out of time.
So you, for proving this, you use, so what you showed us with the, just a degree distribution that many are odd, it's a, enhanced version or version of this, or there's other, what other input goes into the proofs of this?
Right.
Technical
So
theorem?
technical theorem 1 is purely combinatorial. It uses nothing about the max entropy distribution. It actually works even for this Christofides algorithm. And this uses a lot about like the structure of small cuts and graphs and so on. But I think what's nice about it is, pick your favorite distribution over spanning trees, you can use this theorem. So you sort of don't have to worry about crossing small cuts in these graphs. The second theorem is essentially like proving properties like the one I told you about today, the probability that one vertex is even, but sort of generalizing that. For example, what if I have 2 vertices at the same time? What if I want both of them to be even simultaneously? Can we also prove that? It turns out we can almost always prove that, except for some edge cases.
But almost always use a negative association, the negative correlation between. This uses the max entropy distribution and the property that's.
Yes, so the second part is like.
You use log comparison.
Yeah, this is like very crucially, you're going to use properties of max entropy. And this like Bernoulli fact, this Hofting fact, they're both like very crucial in this proof. And we also use this notion that I was going to tell you about, but I don't quite have time, of the capacity of a polynomial that comes from Gurvitz to sort of like make a lot of these statements a lot nicer. So you can take a look at this paper if you're interested in that view.
You think you can say something in a few minutes about the capacity, or why is it good?
Yeah, I can try. Let's do it over here. I mean, yeah, it'll be quite sketchy, but let's say we have 2 vertices. And we want to prove that they're both even at the same time with some constant probability. Let's also assume for now that there's an edge of value 1 between them. There's a bunch of edges here. And like in the previous case, I'm just going to kind of reduce my polynomial to, instead of one that's univariate real rooted, I'm going to reduce it to one that's bivariate real stable. So I might get this polynomial p x of y. And what I really want in this case, for both of these vertices to be even, well, is I want A to get 1 edge in the tree and B to get 1 edge in the tree, because then these both would have degree 2. And you can actually pretty easily show that I take the partial derivative with respect to x, partial derivative with respect to y, and evaluate it at x equals y equals 0. This is exactly probability that these sets are both equal to 1, right? Because this is just picking out a coefficient of x, y in this polynomial. And then there are like 2 nice lemmas. The first is that this thing is at least 1 over e squared times the infimum of this convex program, pxy over xy over all xy greater than 0. And the second thing, this is actually called the capacity of P. And the second thing you can prove, and this is both from like Gurvitz's earlier work, You can prove that if P is real stable and its gradient at 1 is 1 and 1, then its capacity is equal to 1. Okay, so here you would just get 1 over e squared. Yeah, and basically like Griffith's original proof worked in this case that the gradient is like exactly equal to 1, 1. And we didn't really know how to generalize it to the case it wasn't equal to 1, 1. It was kind of like close to 1, 1. And so that's what we did in this paper, mostly Griffiths and Leek, not really me, to be honest. I was more involved in the TSP part. But yeah, what they basically showed is that this thing is kind of stable under changing this gradient a little bit. So they proved, actually this first appeared in an earlier work, Griffiths and Leek, and 22. They proved that the capacity P, at least 1 minus the gradient of P at 1, 1, minus all 1's vector, the L1 norm to the n. So basically, as long as like this thing is pretty close to 1, 1, like at most 1 away in L1 norm, you're going to get some constant bound, like omega of 1 to the n. And this lets you do things like when this edge is not equal to 1, essentially. And then like we expanded it a little bit. Again, mostly them, to be honest. And we proved that actually sometimes it's okay when this deviates more than 1 from the all 1's vector. So we sort of characterize when you still have a constant bound capacity and like this thing is actually greater than or equal to 1, which is actually very important in some of our proofs.
What's n?
Sorry?
What's n here?
N is the number of variables. So I should have said is really the.
You need it only for pairs, the analysis.
We also need it for like 5.
Okay,
variables. Yeah.
It's not.
Yeah. Yeah, so I think I'll stop here.
Okay,
Thanks a lot.
Questions? Okay, so it's lunch.
Yeah,
Thanks
thanks.
a lot.